Chapter 1, we're going to talk about special relativity. In the second lecture, we're going to do relativistic mechanics, which essentially means you bring in energy and momentum to solve problems. The worst possible way that you can solve physics problems is actually using Newton's laws. And one of the reasons why is frames of reference. As soon as you start to go from one frame into the other, you'll see that forces really become an issue. That is not true with conservation of energy and conservation of linear momentum. It's also true for conservation of angular momentum, but we will not deal with conservation of angular momentum in this course that I can think of. There is a little bit that we will talk about, something called spin, later on in this course, but for right now, I won't do that. So what I'm going to do here is that I'm in this first lecture, I want to break it down effectively into pieces. And the first pieces that we want to look at here is that the first one is that we're going to break it up into Galilean transformations. And then what we want to do here is that we want to look at the properties of light. And an experiment known as the Michelson, I know that's spelled wrong, it's okay, experiment. And then we'll start the big process of special relativity. If I was to, maybe I shouldn't have said Galilean transformations. Maybe what I should have said is Galilean relativity. And you're going to see that all of today I'm going to spend on Galilean relativity, because it's super important to getting us to go back and look at what is special relativity. So what I think about it is that I'm going to probably spend all of today on Galilean relativity. Then I'm going to look at properties of light and the Michelson-Morley experiment. And then we'll go into special relativity here. So I guess the way I'm going to, I don't know how to organize this, but maybe I'll call this lecture 1.1. And this is how I'll upload it into Canvas. And we'll talk about Galilean relativity. So if you have questions, I'm assuming that you're just going to just ask. I mean, you could interrupt me. I don't have a problem with that. And then we'll just go from there. So.
Hey, Carlos.
Yeah.
Would the chat box be a good place to put questions too during this?
Sure. That's cool. Not a problem. And then I'll try to, if I see it, yeah, that's actually a really good idea. With the chat box, then I could respond and I could verbally respond to the questions, or if it's important enough, I will, I'll bring up that question in chat just to talk about it. Okay, so
thank you.
Okay, so here we go. So when you look at special relativity, the foundations of special relativity, so I should say this here, so the foundations of special relativity. Now, because special relativity, that word comes up a lot, I'm going to write an acronym for special relativity. And I'm going to define this as SR. Okay, so the foundations of special relativity are 1, Galilean relativity, and then 2, we need to understand the properties of light. And the reason why light is important here is because when you look at the history of special relativity, essentially everything above with Galilean relativity here was due to classical physics. And that's essentially physics between, let's say like 1885 or younger. All of the physics before 1885 is considered classical physics. And what happened here is that around 1885, Maxwell had already written the equations for electromagnetism at this time, but they were being refined. And the guy who really refined it was a guy named Heaviside. And what he did here is he wrote it today into what we now call Maxwell's equations. And so special relativity is essentially trying to ask the question of, is Galilean relativity apply to light? Okay. And so that's why we have to talk about the properties of light, because Maxwell's equations were so new at the time that people didn't know how to incorporate it into Galilean relativity. And it is the generalization of Galilean relativity into special relativity that gives us how light behaves in this new arena here. So, and the key to this here is that it's really motion. Motion plays a really big key. And the way I like to write velocity, and you'll see me write this a lot, is that I'll write this as distance and time here. What you're going to see here is that with velocity here, you're going to see that the key to understanding, special relativity is to really understanding what do we mean by distance? What do we mean by time? Right? These are about as fundamental as you could get, right? These are the most fundamental concepts, right? To move through space and time, clearly that has to be the most inherent thing that we have in our bones here. And so what we're going to find here is that it is Einstein that goes back and looks at distance and time from a new perspective. And it's really that detail that we got to spend a lot of time on. And the only way to do that is we have to talk about these things called frames of references. And that is the key to understanding Galilean and special relativity. So obviously, I'm lecturing here from home. They don't even let me in my office. For me to go to my office, I have to ask permission from the president of the college. So when I'm recording this, you're going to hear dogs shake, bark, people walking, people talking. I mean, I'll tell them to be quiet, but just note that there's going to be noise and shit like that. Okay, let's move on. So here we go. So the first thing that we want to talk about then is the principle of Galilean relativity. So when you look at this principle of Galilean relativity, the first thing that you're probably saying yourself, it must be because of Galileo that actually came up with this. Well, it's actually not true. Newton is the guy that wrote this stuff down, but Galileo had intuition about this. And, he wrote a little bit about it, but it is really Newton who really nailed it down. And this is what it says right here. It says this: the laws of motion are invariant for all inertial observers. And this guy here is so simple, so deep here. Now, let me make sure that I explain this. So when they say the laws of motion, what they really mean is Newton's laws. And when they say invariant, what they mean here is that they're the same for all observers. And the word inertial is about a frame of reference. Now, this is another phrase that comes out so much, frame of reference, that I'm going to define this as FR, because you're going to see this all the time. Okay, so the two acronyms are SR for special relativity, FR for frames of reference. Okay. So what I want to do here, okay, I want to go in and I want to start talking about this. And I'll explain what do I mean by inertial in some detail, but you should have seen this already in great detail in your Physics 4A class. So now let's go and look at this guy right here. So what we want to do here is that because frames of references are so important in special relativity, so that means in lecture 1 and lecture 2, and that means in 2 quizzes and 1 exam, I'm going to try to hit you as hard as I can on frames of reference. So you have to have the understanding of frames and references in your bones, because you're going to see, maybe I should do a quick side note right now. This first chapter is conceptually challenging, like really challenging. And this is what you're going to see here. So if I was to just give a quick aside of what do I mean by this, the main equations in special relativity look something like this. A equals BC. And you know what's going to be crazy? That B right there is going to be given. So then when you look at the questions, you're going to say, well, is it A or is it C? And my experience over the years here is that the majority of you are going to fail in solving A equals BC. And the reason why it's so conceptually challenging, because you don't understand from what frame of reference you're speaking from. So when I say that frames of reference are super important, they are. And sometimes on these examples, I'm going to be, I'm laughing a little bit here, but I don't mean it in a bad way. But what will happen here is that you'll see me go sort of like, okay, I now have B. We now know that what the problem given you is A. Let's solve for C now. And some of you are going to say like, I don't get it. What's my point again? You've got to come from this from a conceptual viewpoint. If you come from it from a mathematical viewpoint, you're going to get into trouble. I promise you. So it's not about the mathematics. It's about the conceptual framework that you approach these problems. So the first thing that I want to ask then is, what is a frame of reference. And remember, FR is frame of reference. That's what I want to go after right there. So a frame of reference, so a lot of the times you'll see me say a frame of reference is your point of view. And that means that everything like in your room, your chair, your bed, your sofa, your table, whatever it is that's in the room, they all share your point of view. Or they share the same state of motion. And one example that I could think of here is I could imagine that I have a plane. And for the sake of argument, let's say that this plane is traveling at 500 miles per hour. Now, when I look at this plane here, when we say 500 miles an hour, one frame of reference is that of Earth. And if you're in this plane here, well, from your frame of reference, this person in the plane here, what I say, when you say your frame of reference is in this plane, that means that all the seats, people in the seats, magazines, a cup, or whatever it is that's in that plane, that's your frame of reference. And as far as you're concerned, you are at rest in that plane, even though the plane is moving 500 miles an hour. If I had another observer over here on the ground here, to that observer, that frame of reference of the Earth, we would then say everything there was traveling at a constant 500 miles an hour. So even though you are moving at 500 miles an hour, you don't feel that you're moving at 500 miles an hour because you're following Newton's first law. There's no net force acting on you, and so therefore you feel nothing. And we'll talk about that a little bit more here. So when I talk about a frame of reference, it's the frame of reference of the Earth, in this case, or the frame of reference of the person of the car or of the airplane. So then the question that we should ask then, what is an inertial frame of reference? And a lot of times when you hear me talk about frame of reference, I'm really talking about an observer. Okay? So if I say, what is an inertial frame of reference, or what is an inertial observer, they're really one and the same, because to make a measurement, you're an observer. To make a measurement, you need a frame of reference. And so what we do here is that the way we talk about it here is that we talk about it in the language of Newton's laws here. And so if I look at Newton's first law, and just as an acronym, because I've been using this forever, in case I write this down, I'll write Newton's first law as N1L. If I'm talking about Newton's second law, I'll write that as N2L. So it's Newton's first law. Newton's first law defines the coordinate system where Newton's laws are valid. Okay? So according to Newton's first law, they define what is an inertial coordinate system. And what we find here is that this coordinate, you have to be in what I call a natural state of motion. So if you're in a natural state of motion, that means one of two things. That means you're at velocity equal to 0, which means at rest, or you're moving at constant velocity. And so what you find here, if you have an observer that's in a natural state of motion, either at rest or moving at constant velocity, then this is what we say here. Excuse me, a inertial observer has force-free motion. And what do I mean by force-free motion? So then from Newton's second law, what we say here is that the net force must equal mass times acceleration. But if you look up here, the acceleration in each of these cases is 0. So if that's 0 here, then this means this is 0, which then means that the acceleration is 0, which then means that you're either at rest or moving at constant velocity. So an inertial observer must be in a natural state of motion. And what this is really telling us is that if this is true here, that means that one cannot tell whether one is at rest or constant velocity. So inertial observers are in force-free motion because the net force is 0. And because the net force is 0, you cannot tell whether you're at rest or at constant velocity. So now we have an inertial frame of reference. That means if an observer is in a frame of reference that's at rest, and I have another inertial observer that's in a frame that's moving at constant velocity, then Newton's laws are applicable. And so any observer in those frames will be able to, apply Newton's laws. And so now we can write the Galilean relativity principle in more detail here. So now if I come back up here and I'm going to try to write it, technically the way it's written here. So this is the principle of Galilean relativity. And unfortunately, you're going to see that I'm going to repeat this a lot. And I figured that if I repeat this a lot, you'll get a little bit brainwashed and you'll know exactly what I'm talking about. I know that that's not true, but repeating this stuff again and again will really help, because remember what I said, this is hardcore. This is super important here, and getting this frame of reference right here. Okay, I want to see, am I seeing any chats? Did anybody send any messages?
Yeah, I was wondering, so is this kind of saying how the frame of reference defines if you are kind of moving or if everything else around you in the universe is moving?
It's actually saying just the opposite. I think that was Matthew.
Oh, yeah.
Yeah, welcome, Matthew. No, it's saying that one cannot tell, and you'll see, I'm going to go into some detail here. Okay, when I go into this detail, you're going to see that that there's no experiment that you can do. But I'll come to that here in a moment here. So, you know what? I am not seeing the chats pop out. So if I look at these chats here, give me a brief moment here. Because if they're private, I want to keep them private.
Okay.
So just to answer, office hours are going to be held Zoom or email or email. Yeah, there's a couple of private messages, so I won't address those. Okay, so I'm going to stop sharing screen. I'm going to go back and.
Hey, Carlos.
Yes.
When you were talking about natural state of motion, you had two arrows and you had velocity equals 0 rest, and then you wrote velocity equals 0.
Yeah, see, I'm just trying to make sure you're paying attention. I didn't put that slash in there. You're right. There should be a slash.
Okay, thank you.
Okay. Thank you for the help there. So then if I was to write this in detail now, it then says here, the laws of Newtonian physics are invariant for all inertial observers. This is what Newton actually wrote right there. So then the question of special relativity then is known, it's the principle of special relativity. What it says here is that Einstein is going to take this and he's going to say, instead of the laws of Newtonian physics, Einstein extends it and says the laws of physics, all physics, including electricity and magnetism, are invariant for inertial observers. And what our whole goal is, to extend Newtonian physics to all physics. But you're going to see that there's some glitches along the way, and they're not small glitches. It's literally changing what we mean by distance and time in order to really answer that question here. So once again, this is Newton that wrote that down. So if I was to sort of like expand this to the airplane that we were thinking about, that says that the laws of physics, okay, so extending this, so if I extend this to the airplane example, what this means here is that the laws of Newton work equally well to an observer on Earth. Because the person on the airplane is traveling at constant velocity at 500 miles an hour, the laws of Newton work equally well for that moving airplane. And what that means here is that the person on the ground at rest relative to Earth cannot say that his frame of reference is the best frame to doing physics. Or the person on the airplane cannot say that his frame of reference is best for doing physics. That according to Galilean relativity, they're both right, even though they have different viewpoints. And so what I want to say here is that no experiment can be done to determine whether an observer is at rest or moving at constant velocity here. No observer can do that. This is such an important concept right there. You can't do a single experiment to determine whether you're at rest or moving at constant velocity. And I've done this, I've said this in many of my Physics 11 and Physics 4A classes in the past. And it's an example that I give here. And this example was, I drove to Home Depot in Salinas one year. This was before they had a Home Depot in Watsonville and in Santa Cruz. And this is what ended up happening. I got off the highway and I'm on a ramp and it's like 6:30 in the morning. And I'm at the light and there's this truck next to me. And I'm kind of waiting for the light to change here. And then all of a sudden, I feel myself moving. And so I slammed down the brake as hard as I could, you know, kind of freaking out. And then I found out that it was the truck next to me that was rolling back. I was stationary, but I thought I was moving. It was the truck that was moving relative to me. So in other words, I couldn't even tell whether I was moving at constant velocity or at rest. So to try to stress this point here, I want to do a good example. And, and this example that I want to do, what I imagine here is that I'm going to have two observers. So imagine two observers. And for the sake of simplicity, I'm going to call them number 1 and number 2. So observer number 1, this observer is going to be at rest relative to the platform. Observer number 2 is going to be at rest relative to the Earth. And what we're going to do here is that I imagine that I have a platform right here. And this first observer here, I'm going to draw in red. And this one's going to be number 1. And then I'm going to have the Earth here. And then this guy here, of course, is the platform. So what we're going to do here is that I'm going to imagine that I'm going to have a device that drops a ball straight down. So if I take my device here, let's say I can hold a magnet, a metal ball. So I could imagine that I have a metal ball right here. And what we're going to do here is that if we have some electronic switch, this ball then will be dropped relative to the platform straight down here. So what I want to look at here is I want to look at two cases here. So the first case that I want to look at, case number 1, I'm going to imagine that observers number 1 and number 2 have no relative motion between them. And so what you're seeing here, if observer 1 and 2, they're at rest, so what's going to happen to the ball? Well, the ball's going to fall down and it's going to hit the ground directly below it. So what we say here is that we say that both observers see the ball fall straight down. Right? Both observers agree. Now what I want to do in this case here is that I want to change it. So now I'm going to do the following thing. So what I'm going to do here is that I'm going to have the same thing again. So let me copy and paste to be faster. So here's my platform again. And what I'm going to do here is that I'm going to come in and I'm going to get rid of this ball here. So I have the exact same setup here, but what's going to happen now is that this platform is now moving at some relative speed here. So that means the platform is moving relative to observer 2. So in this case here, so this will now be case number 2. So now there's relative motion between observers number 1 and number 2. Okay? So the question is, what do they actually see here? Well, for starters here, if there's relative motion in this case here, you could imagine the scenario where this is the ball right here. So if I then come and I click on this guy right here again, and I copy it, I'm going to paste it down here. So if I look at this scenario here, what you're going to see here is that these observers here are going to observe two different things here. In the end, we know that the ball is going to look something like this for observer number 2. So now let's go highlight what you're seeing here. So because of the motion of the platform, observer 2 sees the ball follow projectile motion. So why does it follow projectile motion? Because the platform, even though the ball started at rest in the frame of the platform, according to observer 2 here, the ball continues to move at the same speed as the platform because of Newton's first law. And then because of the force of gravity, it acts on it and it gives it that curved trajectory that we all know and love. So observer 2 sees the ball follow projectile motion. So if I look at observer number 1, sees the ball fall straight down. Okay, it falls straight down. So this person sees the ball fall straight down. And so what you're seeing here is that both observers see different physical phenomena. So what Galilean relativity says is that because observer number 1 is an inertial frame of reference, observer number 2 is an inertial frame of reference, Newton's laws apply exactly the same in each of these cases here. And observer number 1 cannot tell that he's at rest or moving at constant velocity. He sees the exact same phenomena being at rest or moving at constant velocity. Only observer 2 sees a difference because of the relative motion. So if I come all the way back up to the Galilean principle of relativity here, the laws of Newtonian physics are invariant for all inertial observers. No experiment can be done to determine whether an observer is at rest or moving at constant velocity. And what I'm trying to do with this platform here is to show you that that's exactly what you're actually seeing here. So to summarize this thing here, so in summary, and I think this is a really hard concept, statements like I am at rest or I am moving have no absolute meaning. Oops. In fact, it's a meaningless statement to say I am at rest and you are moving, or I am moving and you're at rest. It is politically incorrect, or maybe I should say it's relatively incorrect. You're RC. You're not being RC if you're saying I am at rest or I am moving. There's no experiment that you can do to actually talk about that. So there must be a symmetry between being at rest and moving at constant velocity, which then brings me to my next topic here. So this will be then symmetry. Oh, I think I spelled that wrong. How do you spell symmetry? I think it's like this. Symmetry between inertial observers. So this is playing along the same topic of what we just covered right here, but I really gotta nail this concept as hard as I can. So what I want to do here is that this is sort of like a second conceptual example. And what I'm going to say here is that there are two twin observers. And I just picked random names. And the first names that came to me some time ago is Juan and Maria. So I have two twin observers, Juan and Maria. And so I actually drew some pictures beforehand because I think they're hard to draw. And so the idea here in this example for inertial observers here is that I want to go in and I have my little Juan right here. And I imagine that Juan's in this red spacesuit. And when he's in this red spacesuit, what you're seeing here is he's got a red flashing light. So there's a red light here that's sort of like flashing. So what I want you to imagine here is that you're seeing Juan floating in, I guess, in dark, empty space. So if there's no frame of reference in empty space, Juan feels that he is at rest. Okay, so he's sort of like sitting there. So from Juan's perspective, he's completely engulfed in this complete blackness. And as far as he's concerned, he's stationary from his viewpoint. So now I imagine the following scenario here. So from, you know what, I should change this a little bit. I'm going to move this down just a little bit. And what I'm going to do here is that I'm going to say this is Juan's frame of reference or viewpoint. So now what you're seeing here is that I have a little sketch that I drew over here. And this was just to save time. And the scenario sort of like goes like this here. So off in the distance, so when I say off in the distance, I imagine that this is when he first starts to see Maria in this green suit that is also flashing green light. So Juan sees her off at a distance, and as you see her off at a distance, he sees her as being really small. But according to Juan, she's moving to the right. So as she gets closer and closer, she grows bigger, but continues to move to the right. And then when she gets exactly in the same position as Juan, because they're twins, they're the same size. And so, you know, still sees her moving past him, excuse me, and then recedes off into the darkness. So according to Juan's viewpoint, it's Maria that's moving, not Juan. So if I was to go from Maria's viewpoint, or Maria's frame of reference, according to, you know, Galilean relativity, the exact same situation happens, but in reverse. Maria cannot do a single experiment to determine that she is at rest or moving at constant velocity. So if Maria is going to the right, according to Juan, then for Maria, it's Juan that's going to the left and starts off from far away, moves in, moves out, but no observer can say that they have the right viewpoint. There are two stories that describe one and the same situation from two distinct but equally valid points of view. Maybe I should write what I said. I'm not really sure what I said, actually. I think it said, so there's two stories that describe the one and same, this is the important piece, the same situation from two distinct but equally valid viewpoints. And remember, when I say viewpoints, I also mean frame of reference. And you're going to see when we start solving special relativity problems, people are going to have a problem like, do you mean Maria's frame of reference? Or do you mean Juan's frame of reference? It doesn't matter. what you're going to find here is that you're going to have to pick one frame of reference and stick to that frame of reference. And then you make the observation to, for this other observer here. Okay. So now we've been talking about, inertial frame of reference. One important difference in these inertial frame of references here is that at times we're going to deal with what are called non-inertial frames of reference. Okay. Non-inertial frame of references here. So what have we set up to now? So if I keep summarizing the same point again and again and again here, what we've said here is that inertial observers cannot distinguish between being at rest or constant velocity. Right? Oh, look at cannot. That's a good one right there. Okay, moving on here. So you cannot distinguish between the two here. That's what we mean by relativity. Galilean relativity. So again, one more time, rest or constant velocity implies acceleration is zero, which means that the net force is zero. And this tells us that you cannot feel any difference. Right? That's what we mean by inertial. So the question is now, what happens if you are in an accelerated frame of reference? Can observers know that they are accelerating? And the answer is absolutely yes. So if I say you're in an accelerated frame of reference, that is the same as a non-inertial frame of reference. They're one and the same. So if I'm accelerating, okay, so according to Newton's second law, what we know here, if the acceleration is not equal to zero, that means you must be doing one of three things. You have to be speeding up, slowing down, or turning. You have to be doing one of those three things. And if you're doing that, then Newton's second law says that there has to be a net force acting on you. Something has to be forcing you, right? That's what I mean by the statement. Something must be forcing you to accelerate. So if something is forcing you to accelerate, then that means the observer feels that change in velocity. So then if I extend this down here, then it says the observer then feels this change in velocity. And what I call this thing that I'm calling feels, what I typically call it is that I call it an intrinsic force. You feel those inner forces acting on you. Now, note that that intrinsic force is a pseudo force. Because this is a non-inertial frame of reference, Newton's laws are not valid. And if Newton's laws are not valid, then they violate the principle of Galilean relativity here. So you cannot, apply Newton's laws in these frames of references here. So what do I mean by these intrinsic forces? I mean this here. What I mean here is that if you're speeding up, what do you feel? You feel like like you're being pushed back, right? You feel yourself like if you're in an accelerating car, you feel your body going back. And so it feels like there's some type of force pushing on you, but there's no force. It's just that you're moving slower than the car, and the car seat has to apply a bigger force on you to speed you up. And if you're slowing down, you feel like you're being pushed forward. So it looks like somebody's on your back and pushing you forward, but of course, that's a pseudo force. That's an intrinsic force. It's not something that's really happening. In that case, what's happening is that your body is moving faster than the car, and therefore you feel you go forward. And if you're turning, it feels like somebody is pushing you sideways. Again, there's nobody pushing you sideways. It's just that according to Newton's first law, you want to continue moving straight, but it's the car that has changed direction. And so therefore, you move towards the door. So if you are in a non-inertial frame, okay, so once again, in summary here, in a non-inertial frame of reference, one can tell that they are moving. So anytime you're in a non-inertial frame of reference, you know that you are moving because you feel all those intrinsic forces acting on you. And intuitively, you have a really good inside feel for this. So imagine that you have a hot cup of tea and you're a passenger in the car and your friend is driving the car. When do you take a sip out of your open cup of hot tea? When you're at rest or when you're moving at constant velocity? Now, because of this, you either could be sitting at a table at rest or moving in your car at constant velocity. However, if your friend, the driver, suddenly brakes really quickly and you try to take a sip of that tea, well, you're going to find that you're going to get hot tea all over you. You start to adjust that cup of tea to make sure that it doesn't burn you. And when it falls out of that, your body feels those net forces as you're suddenly braking. You now know that you're in some non-inertial frame of reference.